we're going to be finishing up chapter 2 in this video. So we had left off, we had just finished talking about placebos and the placebo effect, but now we're going to get into a couple of the different variations that we can have in our experimental designs. When we started talking about experiments, I mentioned that we would be looking at the simplest version first. One manipulated variable, one measured variable. But of course, there are always ways that we can modify this, and these are a couple of those. So first we could look at more than one dependent variable, more than one measured variable. So this would help us obtain a more complete picture of whatever the effect is that our independent variable has on our system of interest. So one of the examples that I can give is from my own research with our black-capped chickadees, as per usual, where we could have sort of one group, instead of having an experimental group and a control group, we actually had two different treatment groups. So one male calls were good and one female calls were good. So our two groups would be exposed to our learning process, and then we could measure one thing, one dependent variable. We looked at their rate of learning. So how quickly did they learn to respond to male calls for this group, or how quickly did this group respond to female calls? That's just one measure, though. We also wanted to measure their accuracy. So, did one of these groups end up learning this relationship better than the others? Is it easier to learn male calls or female calls? We can look at their accuracy at the end. So here, we get two different measures, and we can ask questions about how quickly they learned, depending on what type of treatment they received, but also what was their accuracy? How well did they perform based on the treatment that they received? So two different measures, two different dependent variables, just to give us a better idea of how our independent variable manipulations could be playing a role in that bigger picture. So that's point one here. Our second point is to expose a single group to two or more different conditions. Basically, you would have a single group of individuals who would receive multiple types of treatments. And this is really neat because it helps us reduce the potential for those extraneous or confounding variables. So again, we can hop ahead to the slide for that. And this is where we look at the difference between what we can call between groups or between subject designs and repeated measures or within subjects designs. Now, to take a step back, for terminology, the experiments that we've been talking about so far have mainly all fallen under this idea of a between groups or between subjects experiment. And what that means is that we are comparing differences between different groups. So if I, again, hop between slides a little bit, for those between groups, we have group 1, our experimental group, and they receive treatment 1, exposure to, if we go with our drug example, they receive that drug. We then have a second group that gets whatever our second manipulation is for that independent variable. With our drug group, we were saying that they got no drug. And then what we do at the end is we compare the scores from those who received the drug to the scores from those who did not receive the drug, and we compare the means between those two groups. Hence, between groups. We also say between subjects because we're saying that this group has these subjects and that group has those subjects. They are two separate groups of people. Now from that, you might have figured out where we're going with our repeated measures or within subjects design. But here, instead of having two or more separate groups, now we're saying that people in a group would be given multiple different types of exposures. So each participant gets exposed to all the conditions of our independent variable. So again, back here, we have this group of individuals, and they would receive the treatment with the drug. And then after some time, they would also receive a period of time without the drug. Of course, in these situations, we would want to account for a potential third variable being the order of exposure. So some of them would get drug and then no drug, and some of them would get no drug and then drug, so that we can test if there is an effect of order. If there's no effect of order, then we can just collapse the data and treat them as one group altogether. But we'd always want to test for potential third variables when we can. But yeah, the point here being repeated measures, meaning we are having different exposures. We'd measure what their score is after that exposure, then we'd give them our new exposure, and then we'd give them a measurement after that as well. So we're measuring the same people multiple times just to see what the effect is of each of the treatments that they receive. So it's within subjects because it's all the same people being measured over and over again. And the logic here, when we're talking about how this can reduce the potential for those extraneous variables, this goes beyond just controlling for order. This also tells us that when we have two groups of two different people, then we're saying that these people have certain individual or independent differences. So maybe some of them are a certain personality type, and some of them have a certain IQ score and whatever else we care about. This other group doesn't necessarily match them perfectly. Through our random assignment, we're taking all of those potential differences and we're splitting them up so that we don't end up with sort of predictable variation. So we don't end up with, say, all the high IQ people in one group and all the lower IQ people in another group. We're just saying that there's going to be some variation and we've split it apart. But if we only have one group to begin with, then we don't have to worry about that because the people who are receiving treatment 1 are the same people who are receiving treatment 2. So all of those individual differences, all of that variation because of the people themselves, doesn't change between exposures. We're basically using these people as their own controls. So now, stuff that is unique to those individuals doesn't actually affect the stats that we run. There isn't added variation that we don't control for because them being the same people means that they're controlling for themselves. So this is why those repeated measures designs can lead us to have sort of a reduction in those extra variables. And if it's done right, it can actually lead us to having stronger, more powerful results from our statistics. We get to be more confident in what we're seeing because we've reduced some of the noise in our data. So if it's possible, that can be a really useful technique. I will make note that it's important to keep in mind that not everything can be repeated measures. My favorite example of why this can't always work is what if we wanted to look at two different methods of teaching a kid how to ride their bike? And if we use our normal between groups experiment, we have one group and they are taught using method A, and our second group is taught using method B. What if we wanted to set this up as a repeated measures? You can't. Once the children have been taught to ride a bike, you can't unteach that process. So you can't do both of those exposures. You can't use both methods in that situation. You also have to worry about things, especially with, say, drug trials, where maybe an early treatment has some longer-term effect. So we'd have to ask questions like, how long does the drug stay in the system? Or does it cause any long-term or permanent changes to things like brain chemistry? So you always have to keep that in the back of your mind when looking at these repeated measures designs. But that's one of those reasons why we would usually also keep in mind the order just to see if that plays a role. So that gives us an extra indication, even if we don't know from prior experience. Okay, so that was the first 2 points. The third point here is that we can manipulate more than one independent variable. So we mentioned measuring more than one dependent variable, but we could manipulate more than one thing of interest. And this is really neat because it lets us study interactions. So we know from experience that a lot of things are a lot more complicated than just one particular variable or one particular trait controlling something else on its own. Usually there are multiple factors involved. So if you design an experiment that manipulates multiple factors, you can actually get something maybe closer to what we'd see in the real world. Those interactions can be very useful to understand how things work in the real life. So let's look at an example for that one. And so here we have a study that's set up with two independent variables. They wanted to look at cell phone use. So they have people who are driving without a cell phone and people who are driving while using their cell phone. Clearly the images here are dating when this was done, but that's all right. So that's our first variable. Our second independent variable would be the amount of traffic that's on the road during this test. So low traffic density versus high traffic density. So now we have four groups. So we have people who drive without their cell phone in low traffic density, people who are driving without their cell phone in high traffic density, and then people driving with their cell phone in low density and with their cell phone in high density. So now we have four groups so that we have each of the possible combinations of our two independent variables. So we'd say that each independent variable has two levels within it. You could technically introduce, say, driving with a cell phone, and then maybe driving with a cell phone but using hands-free instead of holding the phone itself. Then we could have three levels for our first IV. But once again, we're keeping it simple, or as simple as possible. And with our results over here, we're looking at the braking reaction time, basically saying how long do people take to react to something coming up on the road in front of them. And I suppose we should mention, for ethical reasons, this was done in a virtual setting. So this was done with a computer simulation. So they didn't actually have people out on the roads using cell phones to see how poorly they performed. But this was done virtually, and we looked at how long it took them to depress the brake pedal when something came up. So a higher score is worse. And then we have low traffic density for these two bars and high traffic density for these two. And the green ones are driving with no cell phone, and the purple ones are driving with a cell phone. And while they haven't included the useful things like error bars or indicators of significance, which are going to tie us into our statistics discussion momentarily, but we would look at this and say, okay, these two bars are fairly close together. If they had error bars, the error bars would likely overlap, and we'd get a label that says there is no significant difference between these two bars. We would also probably have an indicator that says that this bar is no different from either of these two either. So all three of these bars are not significantly different from each other. They're all very, very close together. However, this last bar here, for people who are driving and using their cell phones in high density traffic, they're going to show a significant increase in the amount of time it takes them to brake in response to something in the road. So using their cell phone is very detrimental, but only in high traffic density conditions. Because this only shows up in high density, it's not showing up in low density, that tells us that there is an interaction between traffic density and cell phone use, because that relationship changes depending on not just one of our manipulated independent variables, but it actually depends on both of the variables that we manipulated. You have to be using the cell phone and be driving in high traffic density for us to see this detriment to performance. So those interactions can become very useful because it basically tells us that in low traffic density, there's not enough going on to pull tons of your attention. So you can get by, distracted a little bit by a cell phone or not. But as soon as the pull on your sort of perceptual requirements goes up, all of a sudden your performance will tank. And I wouldn't take this as evidence that, you should drive with your cell phone. This is just possibly completely made up data from one of the textbooks. It's just meant to show that there is an interaction in this situation. And with that out of the way, we can get started talking about types of statistics once again. We had mentioned before that we look at descriptive statistics and inferential statistics. But since we've already done the descriptive side, we're going to focus into those inferential statistics. And the reason is that now we've established sort of how we set up our multiple groups. And now we would look at the question of, is there a difference between these two groups? Is there a difference in the mood score between the group that received our antidepressant drug and the group that did not receive the drug? And our inferential statistics allow us to interpret the results that we got and draw conclusions about whether there is a significant difference between the groups or not. So here are some very basics of how that works. And as per usual, if you've taken a stats class, this is very, very simplified. I'm not getting you to calculate anything. I'm mainly looking to get you to understand the logic of what we're talking about when we say there is a significant difference between our groups. So how are we making that determination? A lot of it is going to be probabilistic. So the first things we need to understand is going to be the concept of hypothesis testing and our types of hypotheses that we would be testing. So this ties back to our idea of generating predictions. So once we have our experimental design, we have two possible predictions. So hypothesis testing revolves around the fact that we have two competing hypotheses. So one of the hypotheses is going to be that the relationship that we're predicting to see is actually happening. The other hypothesis is going to be that the relationship we expected to see is not happening. So they have names that are conventionally assigned. So our null hypothesis is what the name says. It is a hypothesis that's saying that nothing is going on. There is no relationship. So we're saying there is no relationship between our variables of interest in our population. So the drug is not going to be affecting mood in our drug exposure experiment. And we could break that down further and say, okay, there is no significant difference between the mood scores of our treatment group and between the mood scores of our control group. So there is no relationship there. Nothing has happened. And if we want to specify that in a slightly different way, we would be saying that our observations, any differences that we've found between those two groups, it is very likely that they've occurred due to random chance or random error that came from our sampling process. Basically, we've acknowledged that no matter what, there's going to be some flaws here. There's always going to be a little bit of fluctuation, some variation in our data. If there is a lot of variation, then it's highly likely that we could find what look like differences in our groups on the surface that aren't actually real differences. So a quick example of that would be to look between these two bars here, where yes, the purple bar is a little bit higher than that green bar, but I told you that there's no difference between these two measures. And the reason for that being that there is likely some spread to the data. And so in that situation, we're saying that these two are effectively the same. There is no significant difference between the two, meaning that we would have accepted our null hypothesis when we looked at the differences between these two particular groups. So that's the null hypothesis. Our alternative is that there is actually a relationship between the variables of interest within our population. So this is saying that it would be very unlikely for the observations that we got, the means of our two groups, to occur due to chance. This is very unlikely to have happened unless there really is a relationship. And so from that conclusion, we'd say, well, if we got very, very rare results, if we made the assumption that there's no relationship, then we must assume that there is a relationship and that our results are a result of that relationship. So if things are too different to be explained by chance, like the null hypothesis would have us say, we reject our null hypothesis and we accept the alternative. So what do we use to make that determination? And like I said, a lot of this is made based on probability. So this is a very probabilistic judgment. And so we would say that we assume there is going to be a normal distribution of the potential for error. And this is saying that even if our two groups had the exact same means, there's sort of some room that maybe because we sampled a little bit differently, or one group has a little bit more individual variation than the other, if this is our difference between the two means, we could have people having differences in those scores. And the further away the means get, the less likely it is for them to have measured as different if they aren't different in reality. So we're looking at measurement error. And the further the difference between our 2 points, so again, hopping back to this diagram because it's easier to see. So saying that these two the difference is very small. So it's likely that those numbers are in reality close enough together that we would call them the same. But if we look at these two here, that much, much larger difference between our two means, that larger score, tells us that we're getting further and further away from the center point of our normal distribution. So for the first 2 bars, maybe it's only this difference. But for the second 2 bars, maybe we're looking at the difference from the middle all the way to, say, here, because it was a big difference between means. And we use statistical calculations in the background. And again, we hand wave those because we do not need to calculate them for this class. But if our differences are this large, we would be saying that out of all of the possibilities that we would predict, if there was no real relationship, something this extreme is very unlikely to have occurred. So if this tells us what we would predict if our null hypothesis were true, but we're seeing something way, way off to the sides, way in the extremes, we're saying it's very unlikely that that happened in a situation where there's no relationship. So we make that judgment, and the standard is usually a 5% cutoff. So in this case, we'd say that there is less than a 5% chance that we would get a difference between our groups this extreme if there was no real relationship here to find. Alternatively, we'd be saying that we are sort of more than 95% sure that it's something other than chance that led us to get such an extreme difference between our two groups. And that 5% is just an arbitrary cutoff that's been set by scientists. Sometimes if people are very concerned about certain types of errors, which we'll mention in a few slides, they can actually go with, instead of a 5% chance, they can go with a 1% chance. So if you've seen the standard being P of 0.05 for that 5% odds, you might also see a P of 0.01, or that 1%. And if you use a P of 0.01, we are saying that we need to be 99% or more certain that what we've observed is not due to chance. In that case, we have to be pretty darn confident that what we found is coming from some relationship that we're measuring in our population. But both of those are standards that can be used. Clearly, you've noticed I'm not really acknowledging the units or anything here, and that's fine. I just wanted a normal-ish distribution so we can talk about the intensity of our difference between our means, where the larger the difference between the means, usually the more confident we are that there is really a relationship here to be detecting. And so for more words in slightly different ways to help get that point across, we would talk about statistical significance. We would say it exists when the probability of obtaining a result as extreme as what we got would be very low if the assumptions of our null hypothesis are true. So if we got this large of a difference between our groups, it is very unlikely to have occurred if there was actually no difference between those groups, if there was no real relationship present. So if we say that there is significance, or if there is a significant difference, we reject the null hypothesis, and we say that we are fairly confident that there is a relationship between our variables. We are going with our alternative hypothesis, and we're saying that yes, there is a relationship here. Yes, there is a difference between these two groups. Now, I did mention error momentarily. So we talked about that worry, where sometimes people will get concerned about maybe accidentally concluding that there is a relationship when there isn't a relationship present. So if you think about it, our P of 0.05 as a cutoff says that we would accept there being a 5% chance that we got this extreme value, not because there's actually a relationship, but because there was a lot of variability, a lot of error in our data. So 5% of the time, you would end up with what we'd call a false positive, where we concluded that there is a causal relationship between our two variables, when in reality there wasn't. We just happened to get an extreme score due to chance. So this is sometimes also called a type 1 error. And there are a couple of different names for this, but I prefer using a type 1 error or a false positive because that's the most intuitive for me. So in that case, a researcher might choose, instead of using that 5% cutoff, to go with the more strict 1% cutoff, or saying that we need a p-value that is smaller than 0.01. In that case, we would be sort of 99% or more sure that there really is a relationship here. The one issue with that is that by being more strict, yes, we've reduced our possibilities of getting a false positive. However, we've actually increased a different type of error. And this is type 2 error. And this is when you miss something that's actually there. So if actually, I can go back here. So if we have our curve here, and this is that cutoff for 5%, the yellow is 5% of all the possible scores. If we set 1% arbitrarily over here by that -3, if this is how strict we would be for that P of 0.01 or smaller, if something fell here, it's still fairly likely that there's a relationship, but our new cutoff wouldn't count it. So if there really was a relationship and it was here, but we cut off here, we wouldn't count it as being a real relationship. So that's where we'd have a type 2 error, where we missed a relationship. So we concluded that there is not a relationship between our two variables, but there actually is. We just didn't get to report it because of something to do with how we sort of ran our data. And this can occur not necessarily just from us choosing a more strict p-value. This can actually come from things like problems with your sample, or problems with data collection, and other different problems in that situation. So these can come out from a whole bunch of different ways. But I just like thinking, as we just talked about our p-values, that's an easy way to visualize them. But sometimes researchers do have to choose, are they more worried about false positives, or are they more worried about false negatives? So which one is the worst for us? And we might adjust our p-values accordingly. So that drop to a p of 0.01 usually happens if people are very concerned about false positives. So yeah, a bunch of stuff can go on in the background there. I have this here as other considerations, but I'm actually going to skip this slide because it comes up again in a couple of slides. I had intended to drag it to where this second version of the slide is, but somehow ended up copying it instead. So we're just going to skip it here and then come back to it. Because I wanted to talk about our pros and cons of our experimental research first. So what are the pros? Obviously, we've been stressing that experimental research is fantastic for getting causality. We want to know the cause and effect relationship between these two variables. And because of our manipulations and because of our controls, we are able to make those conclusions. the cons actually relate to some of our issues with all of those controls. So some people would argue that controls in experiments mean that the experiments themselves are now very artificial. So the more that we hold constant, or the more that we are sort of eliminating the potential for variation in other variables, the less like things in nature the experiment becomes. Because out in the real world, there are lots and lots of moving pieces that all interact. But if we're holding all of those constant, then we've kind of lost that complexity. So we have to consider, do the results that we collected in the lab actually apply to the real world anymore? Or does it only tell us something about how this works in a controlled environment? And there might need to be follow-up experiments to sort of bridge the gap between the two. There are, of course, also ethical practices or ethical issues and even practical issues. I mentioned the one of sometimes you can't teach people multiple ways of doing something. That is a practical issue. An ethical issue would be something like we can't assign somebody to do something that would harm them. So you can't assign someone to be raised in a low socioeconomic status household or a high socioeconomic status household. You can't assign someone to be a smoker or a non-smoker. There are certain things that you are just not able to do. So in those cases, you would have to rely on correlational studies where you can't make something happen, but if it has happened, you can collect data to look at the relationships that exist. We just won't be as certain of causality because of a different methodology. And we'll actually come back and talk a little bit more about ethical issues later on. So the last little bit here for experiments is asking that question of, do we actually trust the experimental results that we got? And what are some of the things that we need to consider in the background? So we're going to talk a little bit about validity first, where in general, validity is just saying how appropriate is some conclusion or decision that we've made, in how appropriate is it in that big picture. And so if we're making some valid claim, then we want it to be fairly accurate, we want it to be reasonable, and we want it to be something that is supported by the data that we got. So we have 4 types of validity that are typically considered, though for the scope of an introductory psych class, we typically pay the most attention to 2 of them, mostly internal and external validity. I will touch on the other 2 on the next slide, but with internal validity, this is asking basically how much our results can be attributed to our independent variable rather than some other explanation. Basically, how sure are we that the difference that we saw in our dependent variable was caused by the manipulation of our independent variable? So in our drug example, how sure are we that the drug group having an increased mood was actually caused by the administration of the drug? Are we sure that it wasn't just their expectations? Are we sure that it wasn't just the passage of time? And if we've controlled for other variables, if we've done sort of due diligence in designing the study, then we should come out with fairly high internal validity, meaning that our results are telling us what we think they should be telling us, that our manipulation caused a specific change in our dependent variable. So now we know that manipulating A causes a change in B. If we have low internal validity, though, that means that we didn't do a great job controlling other variables. So in that case, we're actually not sure that the results were actually caused by our manipulations. And if the whole point of our experiment was to determine the relationship between our IV and our DV, having low internal validity basically just says that the entire experiment doesn't tell us much at all. So if you have low internal validity, you kind of have to go back to the drawing board and try again. Because you can't make any further conclusions if you're not sure of what you found to begin with. If you have high internal validity, if you're pretty sure the results are telling you what they're telling you, then we can move on to our external validity. And this is the degree to which our results could be generalized to other people across settings and across time. So when we're talking about generalizing, we're talking about applying those findings in different environments. So we conducted a study with this drug trial on Edmontonians, but does it also then apply to people who live in Calgary? How about Toronto? So if we think that it would apply in all of those places, maybe because of some of our sampling methods, or maybe there was replication and agreement with some other studies, we would then have better external validity. So usually external validity is tied to either having a representative sample or by having that potential for replication. So any of those considerations we discussed when looking at getting a representative sample, or what bypasses the problems that come with an unrepresentative sample, those all help increase our external validity. So high external validity means that we can apply our findings to more situations, to more groups of people, to more different periods of time. Low external validity would mean that our results only apply to the sample that we got the results from, and that we wouldn't be confident in spreading that out and applying it to anyone else. So we would like to have high external validity, but it isn't always possible, once again, depending on what type of sample that we had. And as I said, there are two other types of validity that are often mentioned. So this slide, I've actually borrowed it from my methods course that I teach, hence the sort of notation of where it's come from down here. But they mention construct validity and statistical validity as well, where construct validity is looking at how well the variables that we've used in our study, the ones that we both manipulate and measure, how well they are actually measured and manipulated. So if we have high construct validity, then we know that our measures are going to relate to the concepts that we're trying to study. So is our mood measurement a good indicator of mood? Is our manipulation of getting the drug or not getting the drug? Are we certain that those in the drug group got the drug? If yes, then we have good construct validity. If there's potential for uncertainty, that then lowers that construct validity. And then statistical validity can be thought about as basically how good are your stats. So this is the extent to which our data supports the conclusions. So we can look at things like the strength of our association. We can look at the statistical significance and things like that. So did we get statistics that support our conclusions? If yes, we have statistical validity. And our stats, whatever our outputs are, usually p-values and a few other numbers, those are going to tell us that yes, this is a good conclusion to be drawing. Oops, too far. And now we get back to our other considerations of reliability and power. Reliability is looking at how reliable or consistent our measurements are. So if we have a reliable form of measure, it means that if you measured the same thing over and over again, you should consistently get the same reported value. So if you have a reliable measuring tape, then somebody's height would always be measured about the same. You might have a little bit of error because of, say, researcher error. So in their way of getting the measurements, you might vary by a millimeter or two each time. But for the most part, the numbers should be fairly consistent. So we'd have high reliability. Another term that you may have heard is the concept of power. And this is basically saying how best way to say this. So I guess we'll read it. How certain are we that we could find a relationship in our population of interest if there was actually a relationship to find? So having a high power for a study means that if there was a relationship between our two variables, we are very confident that we would get results that tell us that there is a relationship here. So what this means is if you have a study that has high power and you didn't find a relationship, we would be pretty sure that there isn't actually a relationship in that population, because if one was there, we would have found it. Whereas if we have really low power and we don't find a relationship, then we might have not found it simply because our study wasn't the best way to look for it. We aren't sure that not finding the study or not finding the relationship actually tells us anything about this situation. So having high power is usually really important because if we find something, then great, we found it. If we don't find it, then we would say that it's probably not there to be found if our power is high enough. And I guess the easiest way to visualize this is if you have less variation or less noise in your data, your power tends to be higher. So one of the easiest ways to increase power is actually to increase the number of people in your sample. So the more people that you sample, the clearer it is when you start looking for differences between groups. So if you have that ability, having a larger sample size can be really helpful to increase power, to increase your certainty that if there was a relationship, you could find it. There is, of course, always the possibility that due to some kind of limitation, whether it's your methodology or access to participants, it's not always possible to increase your number of participants. So sometimes you might have to use things like different types of statistical analyses to help with power. So maybe you'd use a repeated measures study so that we have less noise in our data, so that you'd have higher power for the same number of participants. There's all sorts of different ways that you can do it. But it's been I guess, not so much recent, in the last 2 decades or so, there's been a really big stress on reporting power as well when you present your results, especially when you present results where you've accepted the null hypothesis, where you've said that there isn't a relationship. Because reporting no relationship with a low power doesn't necessarily tell us anything, but no relationship with high power tells us that there probably isn't a relationship. So it's a good value to keep in mind and to report when presenting research, or I guess to keep in mind when reading research as well. In the last little section here, we get into the very briefest discussion of ethics. Now, you can take entire courses on ethics, so this is just meant to be a sort of reminder of this is something that exists. Here are some basics and some maybe important resources to look at if this is something you're interested in. But I always acknowledge that this is a very, very shortened version of a discussion of ethics, and it's just meant for awareness rather than a full education. But with psychology, there are probably a couple of the famous classic psychology studies that you may have heard of before. And a lot of the ones that are very famous are usually that famous because of some kind of notoriety. So maybe you've heard of the Tuskegee syphilis study, or the Milgram obedience studies, or the Stanford prison experiment, or the Little Albert experiment, the Bobo the doll experiment, or even Robber's Cave. These are all very classic psych studies. I mention them in either 104 or 105, sometimes both, but each of these has some aspect that was unethical. Though most of these occurred far back enough, hence them being classic studies, that they existed before we had strict rules that guide our ethics. So in a lot of these cases at the time, they weren't necessarily against the rules. However, they caused enough problems or led to enough harm that people came together and actually made rules and regulations and guidelines for the ethical consideration of individuals participating in research. So we're going to actually look a little bit at those rules. But I suppose first, if we're talking about ethics, what do we actually mean by the term ethics? Ethics is referring to a set of general principles about how people should be educated and treated and respected when they participate in some kind of scientific study. And this is a very science-shifted definition of ethics, but it makes sense for the course. One of our important sort of starting points is the Belmont Report. And this was a sort of a grouping, a conference that was held at the request of US Congress after there was a large outcry against a bunch of those unethical classical experiments. So people were looking at the harm caused to some of the participants, and they said, we need to do something about this. We need to make a list of regulations. So they met for the Belmont Report. And this wasn't just scientists. This was scientists and physicians and ethicists, people who study ethics, philosophers, and even general citizens. And they all met in 1976. The year doesn't really matter, but it helps with timelines for those who like them. But they did a whole critical evaluation of all of these ethical principles and what they thought that researchers should be following when they worked with human participants. So this came out of all of those unethical practices from previous years and that sort of tipped them over the edge. And they proposed three main considerations. So we have our respect for persons, the principle of beneficence, and our principle of justice. And I actually broke these down to get their own slides. But for our respect for persons, we're just saying that people should be treated as autonomous agents, individuals with free will, and they should be free to make their own decisions. And they should be able to make educated decisions. So this is where the concept of informed consent comes in. So we need to give them information about the potential risks and the potential benefits of the research. So what is it that could happen, and is it good or bad for this individual? Also, is it good or bad for maybe the community that they're part of? This is really important. And it needs to be presented in a way where they are not being coerced into participating. And we also have to acknowledge that some groups don't have as much autonomy as others, so they might need special protections. So children, individuals with developmental disabilities, and even prisoners, for different reasons, may not be able to give informed consent. So for our first two groups, we would need the consent, the informed consent of a parent or guardian. For prisoners, we have to worry about the fact that while you're in, say, a controlled environment and where there is a clear hierarchy, if you have a prisoner and a guard tells them that they have a chance to participate in a study, the prisoner may agree to participate, not because they want to, but because they're worried about any pushback. Maybe the guards will treat them poorly for saying no, or something like that. So we need to take extra steps to ensure them that there is no penalty for not participating, so that they don't feel coerced into the act. So that's our first principle. Our second principle is that of beneficence, and this says that our researchers have to take precautions to protect our participants from harm as much as possible and to ensure their well-being. So we, as researchers, need to consider potential risks. Have they given us any information that might get out and, say, connect them to this study? And if so, how do we assure them that it's protected? So we can do an anonymous study or a confidential study. Anonymous meaning that none of the information is linked, or none of their information is actually collected. So this would be a survey where they get your opinion, but they never collect your name or contact info. A confidential study would be that they take your information, but it's protected from access from anyone else. The research participation goes more with the confidential aspect because they need to collect information in order to give you participation points. However, they separate your name from your data through some randomly generated number in the middle. So the number is only ever associated with the data. Your name never gets directly associated. So we take steps to protect identity. We also have to consider potential benefits. So that kind of ties into our informed consent, but we want to make sure that the participants know that the outcome of this result might be useful for you or for those in your community or for humans in general. And we also want to make sure that people are aware of both of these, and it should be explained in very clear ways. And the last principle is that of justice. And so here we are looking at making sure that those risks and benefits get equally distributed between all the groups that could potentially benefit. So in some of those early unethical practices, so for example, if you looked at the Tuskegee syphilis study, this is when the researchers ended up primarily targeting very low income, mainly Black neighborhoods. And they had individuals in those communities participate in a study where they thought that they were receiving treatment for syphilis. But in fact, they were just being observed to watch how the disease progressed. However, when they finally started learning about syphilis and eventually cured it, though there's a whole bunch of weirdness that goes on in the background of how awful that study was, the benefits weren't necessarily applied to the group that had taken all the risks. So other people were receiving treatment for syphilis, but a lot of those in the study itself weren't treated until years and years after the treatment was discovered and sort of perfected. So there's a whole lot of situations where that was a very unjust scenario. And so nowadays, you have to have people in all the groups that could benefit should all also be taking on some of those risks. So no one group shoulders all the risks and no one group reaps all the benefits. It should all be equally distributed. Now, the 1970s was quite a while back, but there have been updates since. So one of the most recent large overhauls was the APA Ethical Principles Update. That happened in 2002, and there have been small revisions ever since. But mainly what they did was they took that principle of beneficence and they split it up into now 3 subcomponents. So that you still want to be treating people in the ways that benefit them and try and reduce suffering. But this also says that we have trying to think of the right word here. As a researcher, you have certain ways that you should be behaving. So you have to conduct good research. You have to have good conduct. You have to be accurate and truthful and honest in the role that you take on. So these are a lot about what the researcher should do in their own way, not just for how they would interact with their participants. So very, very similar, just split up a little bit more in case you're interested. And the last little bit here is where we can look at what are some of these sort of considerations nowadays. So this is from the American Psychological Association. They actually have 10 specific ethical standards, and of those, standard 8 is the most specific to psychologists as researchers. So we have to have these institutional review boards. That's a neutral third party who's going to be looking at our proposals for research to ensure that we're not violating any of these ethical considerations. We need informed consent. We need to know that if we need to deceive our participants, if we can't give them all the information when we get informed consent, if we have to lie or sort of not tell the whole truth, then we need some neutral third party's approval that withholding that information doesn't have the potential to cause harm. Or if it does cause harm, that it is mitigated or overcome by the potential benefit. Usually that leads to us sort of warning them of the potential for harm, but without telling them specifics of the source of it. And anytime there's any kind of deception, you need to follow up with a debriefing where you tell them what information was withheld and why, and anything relevant after the fact. In practice, you will almost always see a debriefing anyways, just because it helps you check in and make sure that no one is sort of negatively affected by the research after the fact. We then have rules for what happens if you violate ethics, what happens if you fabricate data, what happens if you plagiarize. And there are all different massively impactful things that basically ruin a researcher's career, saying that it doesn't seem like a huge deal on paper, but in reality, if you don't follow ethical rules, you don't have a career as a scientist. And because this is something that is a sort of North America wide, and every other country has some version of this, you're going to end up not being able to do research anywhere. And then they also have a small section that covers animal research. So anything that is non-human research, that gets its own cover as well. And just very, very quickly, they have those legal protections for non-human animals. And they focus, because you can't do things like informed consent, so they focus on replacement, refinement, and reduction, the 3 R's. So replacement, could you use something other than the species you've proposed? So instead of using monkeys, could you use rats? Or could you use an artificial neural network and not need animals at all? Can you refine the study itself? Can you reduce the amount of harm that's being caused? Can you make it more effective or less fear-causing or whatever? Can you make the study any better so that it's not causing distress? And then reduction, could you use fewer animals? And this usually involves doing a power calculation and using the smallest sample size that you can while still having a reasonable power for your study. So we have this sort of ethical balance between the welfare of the animals, their rights, as well as the potential benefits that could come out from that research. And of course, all of this, just like with our human ethics, is fed through that neutral third party that makes those decisions by reviewing research before it ever starts. So these review boards are going to control both human and non-human animal research. And so our conclusion for the ethics section here, we're basically saying that we're trying to balance our priorities. We acknowledge that there can be some situations where information may need to be withheld. So we follow up with explaining why it was withheld and sort of any other follow-ups necessary. For the acknowledgement that yes, there might be the need for something that is uncomfortable or distressing or even painful, but the benefits that could come from that research are going to outweigh those negatives to begin with. And all of these balances, these aren't determined by the researchers. Once again, these are determined by those review boards. So we have a neutral party doing this weighting of pros and cons to make sure that we're never causing more harm than we are sort of having that potential for benefit in the future. So yeah, we weigh the potential for harm with the potential for knowledge that we can gain and the contributions to science as a whole in the future.